Hi guys, it's me. If you're watching this, then that means I have been selected for a jury, and so eventually I hope to see you again, because it feels like it's been a trillion years. But fortunately with this lesson in particular, it's really just an algebra skill rather than some crazy calculus thing, and so just following through with a couple of examples and then trying some on your own should be sufficient, and then someday I will come back and we can work through some of these together. But partial fractions is something that we wrote on your flowchart and then just kind of ignored it and it wasn't on the quiz. But partial fractions have to do with rational expressions and splitting them up. So to start with, as usual, let's go to something that we already know. What I would recommend is just to, in a moment, pause the video, try this out on your own to simplify that addition problem, and then hit play and make sure that you've done it correctly. So go ahead and pause now to try it. And welcome back. But basically, we just want to make sure we get a common denominator. So this denominator here can't be factored any further. Second denominator can't be factored any further. So our common denominator just needs both of those. So the first fraction has an x in the denominator. It needs an x squared plus 1, so I'll do that. But since I multiplied the denominator, I do the same to the numerator, because then I'm not actually changing anything, because I'm multiplying by 1. That was my cat meowing. Hi, cat. The second fraction already has the x squared plus 1. It needs an x. And so then it's just a matter of multiplying this out. So first fraction is a 5 and the x squared plus 1 with our common denominator, plus an x and the 3x plus 2 with our common denominator. And so now that we have the common denominator, we can just start multiplying stuff out and sticking it together. So I have 5x squared plus 5 from the first fraction, and then a 3x squared plus 2x from the second fraction, all over that common denominator. So then, just combining the numerator, 8x squared plus 2x plus 5. And I'm leaving my denominator in factored form just because I know where I want to go when we start doing this backwards. But the idea here is that what you've done in the past is that you've been given 2 or 3 or 4 pieces and you have simplified them into a single expression. What partial fractions let us do is go from the answer, which is a fairly complicated looking expression, back to the separated version, which is going to be easier for us to integrate. So that's an old simplifying problem. Let's take a look at doing that in reverse, which is what partial fractions are all about. So here, for us to have ended up with this as an answer to a simplification question, really to an addition question specifically, we must have had a denominator of x, and we must have had a denominator of x plus 2. In Calc BC, we are fortunate that we only have to do the simplest type of partial fractions, which is called non-repeating linear factors, which really just means that there aren't any exponents to deal with down there. So linear just means nothing's quadratic. So it's not like an x squared plus 2 or the x squared plus 1 we had in the previous problem. You have to make some adjustments for that. It's not in the BC curriculum. We've missed enough days at this point, so I'm throwing it out. The non-repeating business just means that each factor appears only once. If you had an x plus 2 squared in the original, this problem becomes a little bit more complicated. And again, I'm just throwing that out because we don't have to do it. So here, when we're dealing with non-repeating linear factors, that's the easiest type because that means that our numerators in both of those fractions are going to be constants. As soon as exponents start getting involved, sometimes the numerators aren't constant and that becomes tougher. So to say that they're constants, usually we just use capital letters, do a capital A and a capital B. That is my stupid cat again, so welcome to my life. So then what we need to do is just to make sure that this equals that. So now it becomes a simplification problem. So my first fraction needs the x plus 2 to get that common denominator of an x and an x plus 2. My second fraction needs the x. If you're not totally clear what I just did there, I just put an x over x for this fraction, and an x plus 2, and an x plus 2 for that fraction. And once again, we want to make sure that this fraction equals the original. And because our denominators are completely identical, we can, I guess you could say, multiply both sides by x times x plus 2. And since the denominators are the same, that just means the numerators need to be the same as well. Once we get to this point, there are a couple different options for how to proceed. This one is pretty easy to do the way that I was taught, and then in a moment we'll take a look at what happens if that method isn't so easy. So here, what I'm going to do is just multiply out the left side. So I have ax plus 2a plus bx equals x minus 6. I sure hope you're hearing my cat. That is weird. And then I'm just going to focus on coefficients. So on the left-hand side, the x terms, or the linear terms, have coefficients of a and a positive b. On the right-hand side, that term has a coefficient of x. So I'm just going to set that up to say my x terms, if I combine those guys on the left, the coefficient would be a plus b. On the right-hand side, that coefficient is a 1, so I know that the sum of my constants has to be 1. The other thing that needs to be true is that my constant terms have to be the same. So here I'm doing my lousy notation just to say it's a constant, it's not a variable. 2a equals negative 6. And on that note, when I say that it's a constant rather than a variable, sure, a is a letter rather than a number, but remember, it's just a constant that we don't know. X is something that's changing, whereas a, I don't know what it is, but it's not changing. So it is a constant, so I'm going to match that up with the negative 6. And at this point, we just have a system of equations that you can solve the way you've always done. If you want to hit pause here and try to solve that on your own, feel free, or you can just follow along with me. The second equation immediately gives us a equals negative 3, and then plugging that into the first, I have negative 3 plus b equals 1, which tells me that b has to equal 4. And so we've done the hard work. It's just a matter of taking our setup from the very beginning and putting in the things we know now. So now we know that a is negative 3. So I have negative 3 over x. Plus, we also figured out that b was 4. So I'm going to plug that in for b. And that is our partial fraction decomposition of our original expression, which was this. If you simplified the left-hand side, that would be, of course, the way to check this, but you would end up with those being equivalent expressions. So here again, all we've done is algebra, but what we're doing is we're taking this complicated-looking thing and splitting it up into two simpler-looking things. So if I asked you to integrate this thing, you can split it up and integrate two simpler things instead, which is one of the applications of partial fraction decomposition. I am too cheap to spring for the pro version of this, and I'm just about out of time on this video, so I'm going to pause this one and start a new video, which will have a new link on the website for the next example.